When we discussed equations, we said equations possibly could have one of three types of symmetry. One was even, which meant a reflection across the y-axis. One was odd, which was rotational symmetry about the origin. And for equations, we could also have symmetry across the x-axis. When we discuss functions, they can either be even or odd functions, or neither, but they cannot have symmetry across the x-axis because a graph that's symmetrical across the x-axis would fail the vertical line test and it would not be a function. Even functions are symmetrical about the y-axis. This graph, y equals x squared, is an even function because it's symmetrical, mirror image across the y-axis. In general, you can tell a function is an even function that if you substitute a negative value for x into the function, your y value should be the same as when you inserted the positive value for x into that function. For example, when I insert a negative 2 into the function, I get a 4, which is the same as when I insert a 2 into the function, I get a 4. So the test for even symmetry is you put a negative x in for everywhere there's an x, you simplify, and if you end up with your original function, then the function is even. So I'm going to do that with the first example. I'm going to put a negative x in for x, so I get negative x to the 6th minus 2 times negative x squared plus 3. A negative to an even power is a positive, and then x to the 6th. A negative to an even power is a positive, so that shouldn't be a 2, that should be an x. I get x squared, so negative 2x squared. Plus 3, there's no x's to deal with there. And I note that my function after simplifying is equal to my original function. Therefore, the y values would be the same whether I put a negative x in or just an x in. So this one does have even symmetry. In general, if every power in a function is even, then the function will have even symmetry. For odd functions, those are the ones symmetrical about the origin. The cube root of x function, I've drawn a portion of it here. If I put a negative number in for x, I'm going to get the opposite of the number I get when I put the positive number in for x. For example, if I put a negative 1 in for x, I get negative 1 out for my function, which is the opposite of what I put when I put 1 in for x. If I put a 1 in for x, I get a 1 out, and the opposite of 1 is negative 1. That's how you test to see if something has odd symmetry by graphs. In order to do it algebraically, you put a negative x in for x. So I put a negative x in here, minus 5 times the negative x. A negative to an odd power is a negative, so I get negative x cubed. Negative 5 times negative x is a positive 5. Notice that this does not match my original function, but if I were to factor out the negative from this function, I would get a positive x cubed minus 5. This is my original function with a minus sign in front of it, so this does meet the definition of a graph that has odd symmetry. In general, if all of your powers of x are odd, the graph will have odd symmetry. Beware that if I were to add a constant here, it is no longer an odd function because the power of x for that constant is x to the 0, which is not odd. So if I added that plus 4, it would have no symmetry. So let's look at another function. This function is f of x equals x times the square root of 1 minus x squared. I want to know whether or not this function is symmetrical. The way you test whether it's symmetrical is you put a negative x in for x. So I'm going to put a negative x times the square root of 1 minus negative x quantity squared. I'm going to simplify this by pulling the negative out in front of here. 1 stays the same. A negative to an even power is a positive, and that's x squared, and a positive times a negative is a negative. So I get 1 minus x squared. You should notice that I have my original function times a negative sign which meets the definition of an odd function. This function is an odd function. And if you're wondering why it's odd, you can look at the graph of the function. And just a quick sketch of the graph of the function. This function has a domain from -1 to 1, and you can figure that out by figuring out when you're going to get a negative underneath the radical. But in general, this function, if that's negative, it's going to be negative. So in general, that function looks something like that. And you can see that it has rotational symmetry.